Yeah, I'm Nick from Grand Rapids, Michigan. Kind of important facts about me. Favorite beers, all-day IPA from Founders Brewing from my hometown. Favorite Python feature, just like kind of the quick development cycles that we have in it. And in Python 3, there's the asynchronous that came along. It's great. 3.7, I'm not quite sure about my favorite feature yet, but I think like the breakpoint built in is pretty handy. And then a little bit about my employer. I think a lot of you might be wearing the lanyards. Telnix is basically building like a next generation infrastructure for voice messaging and networking with kind of modern APIs that are easy to use. The messaging is bold because it's the most important, and it has nothing to do with that affect them on that team. So, all right. We can basically get into profiling. So, profiling, when do you use it? It's when you don't know why your code is slow. So you have some slow code. It's maybe getting to be a little bit frustrating, and you just want to basically make it faster. The cool thing is that all of you, I assume you all have Python installed, all of you already have a profiler on your machine. cProfile, and also Profile is the pure Python version of it, comes with it. So you can basically take your script, and add -m cProfile when you call it, and it will profile it for you. Let's do it. Let's check it out. So I have like a dumb little Fibonacci script here. It works pretty well. 10th term, 20th, 30th. Except it starts to like chug once I get to 33. Perhaps I don't know why, but right here we can just add -m cProfile. And it will tell us. So I called the Fibonacci function, if you notice right here, 7 million times, and it took about 1.6 seconds. It's a bit strange. Maybe why is that? Well, that's because it's basically the super naive recursive version of Fibonacci. Basically cProfile is kind of telling us what's going on and why it might be super slow, which you might not necessarily get just from looking at this. This is like a really, really simple program, but we can maybe dive into something a little more interesting. So I also have a Huffman code generator. So Huffman coding is basically a kind of lossless data compression where you can have a bunch of binary codes will basically let you kind of compress some data. So here though, we see there's tons and tons of calls that are happening here. So this gigantic table, what it's doing here is listing the number of calls that each function was called, the time it's spent in the function total per call, and then the cumulative time, which would be the time in the function or below in the call stack. Except here, it's kind of hard to figure out why it took so long because there's a bunch of stuff. I don't know, arg parse, great. Kind of the first argument that we can add to cProfile here is sort. So now it'll still vomit a bunch of stuff at us, but if we go up to the top, we can start to see that, okay, it spent a lot of the time doing, regex find all, because it was going through Moby Dick. Read Moby Dick faster than I can in 100 milliseconds. And then it also was using the heap queue and popping items off for about 150 milliseconds. Spent about 84 milliseconds inside that. This is still kind of nasty. I think a lot of you might agree. There's kind of from this table that we have here, there's SnakeViz, which makes it a whole lot easier to work with. So if we just pip install SnakeViz, then we can use basically the third option that cProfile has. We can list them here, the out file. So what we can do is output a file, you can name it .profile. Internally, it's like Python's marshalling a bunch of the calls to this file. So we run it. We noticed it didn't dump all the output to the screen this time. It just kind of told us what the Huffman codes were here and the word counts. So it's like whale, Ahab. This is definitely Moby Dick. And then with SnakeViz, we can basically visualize it. So bam. What are we looking at here? At least to kind of get acquainted. There's two different kind of patterns here: icicle, sunburst. Icicle is sometimes a little bit easier to read. But here it's basically just kind of going through the call stack deeper and deeper. So like the top level function that it called was this kind of built-in, it executed our code within the module, and then here's our main function that is actually within Huff codes. And we see that almost all the time it was in main, it was spending generating the codes. There's like slivers out here. If you look on the left side of the screen, you can see like the name and cumulative time. So it spent about 1% of the time, 5 milliseconds, reading from this IO text IO wrapper thing. Sometimes it can be a little bit cryptic as to like what these objects are, and you kind of need to refer to the code a little bit. But in this case, we were basically just like reading from a file. There's like some other slivers over here. So reporting took 4 milliseconds, probably because a lot of that was printing, and printing can be slow relatively. But in SnakeViz, we can basically just kind of click through here to dig further into the kind of call stack. Within the code book, we're doing a lot of init. So that's basically the like this is within. If you notice on the left again, the directory, that's like an installed package that I have. The subrepo is Huffman, and we can just basically keep digging in. So this kind of shows us like how the code's getting called and where we're spending time. Sorry. So this was SnakeViz. So like when you're interpreting the reports, it's kind of nice to use them as a sanity check as far as, are you spending the time where you think time should be spent? If you see basically a million calls to something that you don't expect, that might be, kind of Python doing something internally to help you kind of get something done. But it might also be a sign that, like you didn't think that the algorithm that, maybe you thought it was simple, but maybe it's kind of exploding in complexity. So you want to consider, can you use algorithmic improvements to make it faster? I say big O for your big N's. Big O is as the number of N's tends towards infinity. Not a lot of us process infinite data. So like it's perfectly fine if you have some inefficient algorithm if you're processing like 5 things. It might have been quick to develop. It's very clear what it is. It's quick to test. So like you don't need to worry about that. And when you profile it, it'll basically show up as just some little sliver that's kind of irrelevant. Caching is also another thing. Caching technically doesn't change the algorithmic complexity, but in Fibonacci, like if we were to cache if we were to basically cache that fib function, the recursion would be practically instantaneous. And then as far as like guidelines when you are profiling, so you should profile a sensible amount. You can, if you have like, let's say scientific code that's taking days to run, don't profile all of it. Basically it'll help you, like if you kind of reduce the input as much as you can iterate on it much quicker. So that way you can see like, okay, I made this change, is it faster? Okay. Plus it stores the stats in memory, and if you're eating a lot of memory, it might kind of just blow up and quit. And then also, depending on the type of code that you have, so if it's scientific code where like maybe your batch jobs are just getting larger and larger, if the code you're profiling is large enough, that'll kind of amortize out, so you don't need to worry about it. But if it's like maybe an application handler, you might have constant time code, but that's actually consuming most of the time. So it kind of depends on the application that you're using or that you're profiling, if you want to, kind of like how this, you should interpret this. Then also just, hitting the biggest nail. We can speed up that pink slice, make it super, super fast, write it in C. But if it goes to 0, we might not even notice. Versus if we spend just a little bit of time on that kind of, lavender slice, we can save a whole heck of a lot of time. And then also, just kind of keep you can keep your slow code around just to make sure that the code that is fast is actually correct. And you can just kind of use tests to make sure that they're in harmony. With cProfile, it's also something where if you're threading or multiprocessing, cProfile only tracks the thread it's in. And then also await, which is something I can show here. Some of the kind of results that it gives you can be a little strange. I can demo that. So with the, sorry. with the Huffman version or Huffman code that I had, I also have like a async IO Huffman codes, and this will go out to So I have a Gutenberg link. It's basically downloading Alice in Wonderland, because we can see Alice said a lot of things. There's a lot of little stuff. So if we actually look at this in SnakeViz, we will see a whole lot of, also like when we're loading things that are not in standard library, all these like slices, so it's finding and loading a bunch of stuff. This might be AO HTTP, but like a lot of this might be some kind of constant time code that we can't really do much about, other than reducing imports. And it's also a little tricky, because if you look at main, we can search for it here, main, and it'll say, it took 114 milliseconds to run. It also has this weird thing where it says that we called main 41 times. We didn't really call main 41 times. With async IO, it's kind of going in and out, depending on how the awaits are working, like especially when it's iterating over a file that might be being read in. So it's a little strange. And then like to dig through it, we kind of need to start like clicking around and then see that main is like way up here. So our main function, which is maybe top of the call stack, is really 7 deep, just in this asynchronous context. And you'll also notice that it says it ran in 115 milliseconds, but that's because it was, that's not counting the actual IO time. So if we go all the way back up the call stack, up here we see select. So that's basically what was actually waiting for IO from the internet. So that actually took, about half a second, but our main function was, about 130 milliseconds. So just, some of the kind of gotchas that you can, might need to watch out for when you profile. Now, we'll do something a little bit more kind of engrossing and organic. So I was asking my friend for some code that he had that maybe kind of took him a little bit of time to run. So, it's like when you're writing code, like don't profile it right at the start. Kind of get it running, get it working, and then especially if you're starting to keep it around, especially if you're doing scientific applications, because you might be writing code that you just throw away. But once you're running it again and again, maybe it becomes important to optimize it. So just kind of so we know what we're talking about, this code's about transcription factors and genes. Transcription factors activate genes. So just so the kind of terminology isn't completely out of left field. So we can pull it up. Kill this. All right. So to start with, I'll just cheat and like hit up a bunch of times. If you gave me this script, which is going to just basically run a bunch of kind of enrichment, like Fisher enrichment tests. So it's something, it's running, but it's also like kind of trivially just like running a bunch of jobs in series. It's taking a bunch of time. So like I basically don't want to wait for this to finish. So kind of like following my own rules, what I can do is just kind of like reduce the input. So here I'm just slicing the input, so I'm just going to look at 2 of them. So save it, kill this. Now when I run it again, it'll just run 2 of them. So this will help us basically iterate a lot quicker. And we can see it basically kicking out data. It runs 1, it runs 2, then it's done. If we want to profile this, again, we just do M. So the M is for a module in Python, if you're curious. So it's basically executing cProfile, the module, as a script. So this will, again, it'll run. And then we can basically pull up the profile file and see what's taking so long. I did not save it to a file, so it just vomited that at me. But you can tell, it's like sorting through this is difficult, so visualization definitely helps a lot. We can see 10 seconds there, but that's not really useful. So it ran again. Now we can actually SnakeViz, kick us the browser open. It's taking a little bit of time to load because there's a lot more calls that were happened in here. Again, we can see that there's a ton of these kind of find and load, import bootstrap. Again, this is kind of code that will amortize to 0 as we run more and more jobs. It's more kind of the stuff over here, main again, that will kind of grow and grow. So we want to basically focus like on main or below. So once we're within here, we can basically look around, like what's taking a bunch of time. When we're highlighting over these things, it's telling us like the percent time, 54%, 54%. But also some of them, like this one, it's getting called in 2 different places, so it'll highlight them together. And then this one we can see is taking 75% of the time. So we should really try to focus our efforts on this. We can also see that if we click it, the reason it's like now down to 2 layers is because nothing is actually, or this isn't calling anything. It's basically sitting in here. It does call append on the list object, but this is definitely something that we want to focus on. So if we can reduce the 75% slice down to maybe even just make it twice as fast, that'll almost make our entire program twice as fast. So now what we want to do is basically take this function. It's telling us where it is. It's in py-diff-exp, utils, and the name of the function on the left-hand side. So what we can do is we can browse into it, try to find it. There it is. And then something that I really like to do, especially once you get down into the kind of like individual function range, we can basically chop it out and then just use IPython to kind of iterate really quickly. Because right here we have the code. It's right in the browser. We hit Shift Enter. It executes it right then. We could add magics, so like time it. And that'll basically help us, just like, change something, see if it works. Change something, see if it works. So, we have this function. We'll basically just load it in. And then something that we want to do is generate some like random data to feed it, so we can kind of get a feel for how long it might take. Because if we give it, like not much data, it'll be pretty quick. So this is basically just some synthetic data that we can generate to feed it. Like this is basically specific to the function. You would just need to generate whatever makes sense for you. And then here we can kind of like monkey with n to like, get it to a time where it's, we're not really like waiting for it, but it also like runs for a little bit of time. So, like when it's running for half a millisecond, that might be a little like volatile. So we can basically just kind of kick this up until like it's kind of obnoxious to wait for it. It's like 500 is like 100 milliseconds. That's pretty good. We don't want to basically be waiting 10 seconds because we're just like bored. So what we can do is actually start to try to optimize it. So we have this kind of fixture that'll load us data, and then a way to time it. So let's try to we can basically try to improve the function to make it algorithmically less complex, or optimize it with like NumPy. NumPy can vectorize a lot of instructions. Just basically we've identified what's slow, and that is the thing we need to make fast. So here, I basically kind of re-implemented it a little different way. So what this function is doing is it's kind of mapping like a gene name to a giant list of transcription factors, and it wants to flip that around. So it's mapping transcription factors to whatever genes those were associated with. I'm sure there's probably like an itertools recipe for this that I'm just like not aware of, but I kind of was hard on myself and implemented it myself. But once we have this, we can kind of basically take the exact same data, 600, and then now it's 7 milliseconds. So it was 346. It's now about 20 times faster. I shouldn't do math on stage. And it's great. And then we can also kind of keep our slow version around again. So basically just to test that we're asserting that what the old function gave us is the same as the new function. So that way, like we're not actually like missing something, or there's some like edge case. Like here you might want to like kind of dig into it a little bit more just to make sure that it's truly identical. Like if this like n starts to shrink, or if something else is going on. But this isn't going to be part of our application. This is just our tests. So what we can do is take this code, just remove it, replace this. And then now, when we profile it, it should be a little bit quicker. Oh, Derp. It's not pep8, but whatever. So it does one, does the other. Feels a lot quicker already. I forgot the number for our last run. I just overwrote the file. Loading. All right, so now you can see that it shrunk a bit. The kind of this pie slice of chaos was over here. Now it's smaller. And again, we can kind of dig into where we were. Main. So this TF to gene dict, you can see that it's like taking much less time here already. So we're faster, and basically being able to I saved my friend about threefold the amount of time. So you can run his gene studies a little bit quicker. So, something else that IPython is also pretty nice at. There's these magics that we were using. Time it is also kind of a slightly better one because that'll like do it statistically. If you notice, it was like kind of bouncing around a bunch when I was running it. Except time it runs it many times. We can also use SnakeViz has a magic within it itself. So we can basically profile snippets of code here. I don't know, do a lot of people use, I guess, Jupyter Notebook out of curiosity? Like hands? Okay. How many of you use Jupyter Notebook but not with data science? Am I weird? Oh, okay. Okay, I'm not alone. Thank you. So here, we're basically just we're basically calling the same thing that we called before, except in Jupyter. And when we run it, it will run it for us, save the profile, and then open up a tab with the data in it. So this is, again, even faster. So you can basically run a bit of code, see what's going on, and be able to kind of iterate on it much quicker. Where am I? All right. So as far as kind of where does profiling fit into the, how do you use it in terms of measuring performance? I view it as between where you're basically monitoring your whole application in production, because that's completely holistic. You're actually measuring the whole thing running with every other service kind of in and around it. But profiling is, kind of somewhere between that and then micro benchmarks. Micro benchmarks is when you're timing the code, like we were in an IPython notebook with time it. The micro benchmark, it's going to tell you how fast that piece of code runs, but not necessarily what in that code is slow. So profiling basically lets you kind of compose a bunch of stuff together and be able to kind of figure out where you need to optimize it, where these micro benchmarks might come into play or might be useful. And then kind of the same thing with monitoring on down. When monitoring starts saying that this HTTP request or this processing this rabbit message, it's just taking longer and longer for some reason, you can basically try to take that handler out and then start to kind of instrument it, profile it, and then see what is actually taking a good amount of time. Something else you can do that I didn't show here is there's a so this is kind of a quick reference. I'll link to these slides. So this is kind of how you do it from the command line. There's also kind of equivalents that are via the Python code API. So let's say if your base call was just compiling a regex, if you want to profile just one line, there's this cProfile.run. cProfile.run context is kind of a little more advanced, where you can kind of inject local variables into it. But then you can also just kind of profile anything you want, between two, enable and disable. So for instance, something that I've instrumented as far as to analyze why a handler is slow, kind of in the middleware of it. So we're using async IO or AIO HTTP, but Django also has middleware. You can basically start the profiler in the middleware and then kind of go to your handler, run it, and then just return, and then kind of disable the handler, or disable the profiler and dump the stats out. So you can actually kind of, if you're crazy, you could do it in production too. I don't know. But yeah, like this is basically kind of a more a way to kind of like target just part of the code, especially in a larger application where you don't care about a bunch of other stuff that's running. And then just kind of, there's a whole world out there of profilers. We were basically focused today on the deterministic. So it's deterministic because every single call that it's doing, it's logging. And then it's also, it's call-based versus line-based. So there's line-based profilers out there. If you noticed, when it was basically telling us that, like it tells us that main took 2.62 seconds, but it doesn't tell us like which line within that was maybe taking a lot of time. It tells us what calls took time, but not which line specifically within it took time. The line here is basically telling us where that function is in the file, not where it was within the main. So like what you might want to do is like sometimes break up your function into like more bite-sized chunks, so that way you're like doing a few more calls. It might introduce a little bit of a penalty, but you can that'll help you profile with the built-in profiler a little bit better. Or you can basically go out and find like a line-based profiler. There are also statistical profilers. Kind of PySpy is one that I've found pretty recently. PySpy is actually written in Rust, but what it does is every configurable time period, like millisecond, let's say, it goes in and it peeks at the Python process, and then it sees like what the call stack is at that point, and it just kind of samples that. So at this millisecond, like this was the call stack, so it was spending time in there. At this millisecond, it was this. And this is something that you can also like point at a running process. So you have, let's say, some Python process running, like maybe an application that you're load testing. You can basically kind of use that to instrument it like live without actually having any special code within it. Memory is a whole other kind of ball of wax. There's like memory is like very, very state heavy. You can kind of like run a loop and then things just keep getting bigger. You can track kind of the number of references to certain objects, and like this type of object is starting to use more memory. Memory profiling is a lot trickier though. That's why memory leaks are much more a thing. So, but yeah, this is kind of the world out there of profiling. I hope you can use it to kind of make your lives a little bit better, so you're not waiting around for things to run. So, thank you. So I left a reasonable amount of time for questions. I think the first question gets a fancy Telnix battery pack. So, you sir. Do we have mics? Yeah, in the middle. Front middle.
Should I go first? Yeah. Do you have any experience monitoring things like G-event or twisted profiling? I mean,
not G-event or twisted. Like I have monitored some AIO HTTP like handlers. That's kind of where I was kind of looking at or that's why I brought up the AIOH or async can be a little nasty. I don't know how like twisted would compare with it, but I think if you have a asynchronous generator where you're kind of bouncing in and out of it a bunch, it might look weird, but you can still do it. So. Just like with threading and multiprocessing, it'll tell you like where you're spending time. In those cases, it just tells you that it's waiting for a thread because it's like locked. So it's not terribly useful there, but you can kind of profile like individual threads if you want.
Hello, thank you for your talk. I'm wondering, have you ever gone the next step and tracked the profiles as the code base changes over time? One thing I've seen done sometimes, one of the most famous cases, some person did this for Firefox, and they tracked memory usage like per build over like 5 years, and you can see this really great graph.
Okay.
But you do seem like you've gone through so much effort already to set up a test harness and get the code out. It seems almost like a waste not to integrate that into like a unit test and log it somewhere. Is that something you've tried or done? I have not done that. I know, because I think Brian, who's going to give a talk tomorrow, he was looking at unladen swallow, which I think is a
it's more of just like a benchmarking software, and it tracks basically the performance over time. I don't know if it does memory. It does memory as well. But that it is like a kind of more reporting type feature to it there, versus here where it's maybe kind of like one-offs. I don't necessarily know how to like compare two sets of profiles, other than kind of just opening them up and getting a feel for what's taking time. Any other questions?
Yeah, I was wondering if you have any experience trying to profile or figure out what's going on with, say, a production system that is misbehaving in a way that would indicate that you probably have a Python problem.
Okay. Yeah, like there have been kind of times where something is, like I see, the like 90th percentile, start to shoot up. In those cases, it's typically looking at logs and then looking if there's like some kind of weird change in input that might have been happening around there. Being able to, kind of having better monitoring around, like when your response times go up, would be really, really great. But it's not fully automated. It's kind of like a, cycle it, like iterate yourself to try to figure it out. And then once you, identify some strange input, just start to like, hammer it in dev or something. So nothing too fancy yet, but I'd love to try to figure that out.
I'm not sure if it's a feature of Profile or cProfile, but can you filter out all standard library, anything that's not your code?
I don't know if you can eliminate them. So like would the fear be that it would just take up like a lot of like memory for to visualize?
Just the noise.
Yeah, like I don't know if there's like a good way to filter it. But if you are like perhaps calling the standard library tons and tons of times, that might be like an important thing to look at and consider. A lot of standard library calls, if they're, I don't think cProfile goes very deep into the kind of C territory. So the standard library calls that basically, just call, like square root, or it's just calling it in C, basically just kind of ends right there. Is that it? Any other questions? Middle? Yeah. Or yeah, sorry. By the divider.
So you were talking about cProfile doesn't go very far into C. Do you have any experience of trying to do sort of cross-language profiling, where you've got sort of C extensions and where the time's being taken?
No. Again, yeah, like I'm like kind of, it's like, yeah, that's not something that I've dug too much into. I'm curious if PySpy, because it's looking at the call stack, I think though it's looking at Python-specific kind of structures that are in the call stack, that if it's C, it won't necessarily be able to figure that out. But that's something to look at. I'm not like, I haven't made many kind of C extensions yet. I don't know how cProfile reacts with Python. So if you're kind of writing semi-static Python, that may or may not kind of show up in the traces. Any other in the middle?
I was just curious from your experience. Have you seen an application that's running under the profiling experience significant performance hits as it runs? Is it something that you would definitely not run in a production environment because of this, or is it, tolerable in certain cases?
Yeah, like the profiler definitely does introduce overhead. With cProfile, it is typically not too bad. It seems to be, because like even the Fibonacci one, where it's making 7 million calls, that doesn't seem to be too terrible for it. Profile is generally pretty slow. Like, profile is, I think if you're like customizing the profiler, you could use that. But it seems like there are certain calls that seem to just take a lot more time for the profiler. I don't necessarily know what they are, but if you can basically validate that your like handler, your message processor isn't too ill from them. That's something that I've been pondering. Is just like a magic bit to like toggle it on and off to dump a few, and then turn it off, kind of restore performance. Is that it? Any other questions? All right. Thank you very much.